Jim, I've been, as a non-quantum physicist, my my doctorate in neuroscience. I have really been passionate about trying to understand cosmology for my whole life. And I know the basics, quantum mechanics, general relativity, but what are some of the most important contributional theories that together can give us an understanding of the meaning of cosmology?
Um, that is a tall question, and people will give different answers to it. I'll give mine,
Good.
right? What's important, right, is to understand our universe, how it evolved, right? What are the laws that govern the regularities that we see in it, right? From the point of view of fundamental physics. That means quantum gravity, and it means a theory of the quantum state of the universe. It needs two pieces, right? A theory of the dynamics and a theory of the state, and then to see what we can predict from realistic theories and test them against what we see of the universe today. It's not really different from from what human beings have been doing for thousands of years, trying to understand whatever the universe seems to them as a whole in terms of basic physical laws. We have a better appreciation today because we're able to do more experiments of the nature of those laws. It's a big extrapolation to apply them to the universe, but a necessary one to continue this tradition, and hopefully we'll be successful in discovering what it is, what theories really compress all the discussions of the regularities we see all over the universe and explain those that aren't the results of that, but are the result of quantum accidents like evolution that occurred over the course of its history. What can we explain, right, and how do we explain it?
So we deal with an initial state and then a dynamic process to have that state go forward in time.
Except for the word initial, I'm with you on this, because there's no time, right? The world is four-dimensional, as far as we can tell, or 10-dimensional according to string theory, or more or less. So we need to understand not only evolution, that comes later. We need to understand the prerequisite for evolution, which is a classical spacetime. What classical spacetimes come out of a quantum universe?
Yeah. What are the importance of some of the areas that you focused on? The wave function of the universe, the Hartle-Hawking state.
Mm-hmm.
How do these big, uh, interesting, original ideas affect that overall philosophy of state and dynamism?
The no boundary wave function and the Hartle-Hawking state are the same thing.
Right.
They tell us that the evidence of the observations of the universe are that it was much simpler earlier than it is now. More homogeneous, more isotropic, more nearly in thermal equilibrium. The light from the Big Bang, right, shows very tiny fluctuations in the order of 1 part in 10,000 in the temperature. Yet those fluctuations were important because the collapse of those fluctuations gave rise to the stars, galaxies, and ultimately the biota and human beings that we see today. So it's this standard effort, I think, of human society to try to put what we see in order. As Bohr said, the task of physics is to extend its range and reduce the phenomena to order. And that's exactly what we're doing in quantum cosmology. We're extending it to the biggest possible range, the whole thing, and we're trying to reduce it to order, right, that explains what we see today.